Hope everyone is comfortable with the RC and RL transients as of now, till now. Yes? Yes, right?
Yes, sir.
So we'll begin the next transient topic, final as well. RLC, a circuit consisting of R, L, and C. RLC charging and discharging transients. All because of DC sources, remember that. Charging and discharging transients. Excited by a DC source. So first we'll talk about charging transient. So I have a source V of t or V in of t, I can say. Resistor, inductor, and capacitor. Simple series RLC. Transient V in of t, either I can have a switching arrangement, otherwise I can say V in of t is a step change going from 0 volts to a 10 volt. Okay, at time t equal to 0 seconds. I can say V in of t a step input, that is 10 volt into U of t. It says that your Vn is equal to 0 for t less than 0 volt, sorry, 0 seconds. And Vn is equal to 10 volt for t greater than or equal to 0 seconds. You can take that way, or greater than 0 second you can take. Okay, so that's your Vn. Simple and formal definition of a step input. Okay. Right. So 0 for t less than 0, 10 for t greater than or equal to 0 seconds. Okay. Yes. So then what is our focus here means there are two parameters. One is the current charging the capacitor or the current through the inductor. Since both are in series, the current through the inductor as well as current through the capacitor are same. Then anyway, whenever we have inductor, the focus is on its current. So current transient through the inductor and voltage transient across your capacitor. That's your VC of t. That's our focus. So we are interested in determining the transient current response of this circuit and the voltage response across your capacitor. We are interested in these two responses. Okay. So now let us play in S domain. Otherwise, what's a KVL governing this simple RLC circuit? What's a KVL? KVL governing this. The supply voltage V in of t at any given time. Analysis for t greater than or equal to 0 second. Assume initially no current through the inductor, that is I of 0 minus in the circuit equal to 0 amps. And VC of 0 minus is equal to 0 volt. That means initially uncharged inductor and capacitor. So there is no energy in the magnetic field. There is no energy in the electrostatic field as well for the inductor and capacitors respectively. Okay, so initial condition 0. That's what it means. Initial current through the inductor is 0. Initial voltage across the inductor is, capacitor is 0. So inductor doesn't have any energy. Otherwise, instead of saying this, they will say no initial energy with the inductor, no initial energy with the capacitor. It means no initial voltage across capacitor, no initial current through the inductor. Under this condition, let us begin the analysis for t greater than or equal to 0 second. The KVL governing this simple, okay, single loop RLC circuit is VR of t plus VL of t plus VC of t. Easy? Sum of voltage drops across resistor, across inductor and capacitor opposes your input, makes your simple KVL. So this KVL should be in balance at any given time from t equal to 0 second to t equal to infinity. Okay, easy, easy, right?
Yes.
So now let us, okay, solve for getting the current and voltage. Okay, so the KVL can be modified as V in of t is equal to I of t into R, that's a voltage across resistor. Voltage across inductor, L into di of t by dt, that's a voltage across inductor. And voltage across capacitor, 1 by C integral 0 to t, because minus infinity to 2 it is, but till minus infinity to 0 it doesn't have any charge, so 0 to t I of t into dt. This is VR, this is VL, and this is VC shortly. Okay, then V in of t anytime is equal to this. Then apply Laplace, we can find the current. Apply Laplace, we can find the current. So Vn of S is equal to S. You'll end up with I of S into R plus applying Laplace transform on both sides. Then it is going to be L into S into I of S minus I of 0 to initial current. Okay, that is taken 0. Then 1 by C into I of S by S. Okay, that's how we get. Then I of S is common, so Vn of S is equal to I of S into the impedance offered by resistor plus impedance offered by inductor plus impedance offered by capacitor directly. We can play in terms of impedance. Impedance offered by directly, this is nothing but your impedance of your total circuit, that is Z of S. One can directly say the total applied voltage is equal to the total current into what? Total impedance also one can say. Okay, if you know this, directly begin from this point. Or if you're starting from the scratch in ODE, okay, we are looking for the ODE by using ordinary differential equation. Okay, it's not only a differential equation, also having an integration. So don't call it as a ODE. We are looking for the equation governing this system, that is your KVL. From the KVL, you build everything. Okay, till this point, it's clear, right? Yes.
Yes.
So that's your current. Okay, so then once again we are interested in, so I of S is available now. I of S is equal to what? Vn by Z. Okay, Z is the total impedance, so I of S is equal to V in of S divided by R plus SL plus 1 by SC. Okay, we'll simplify this. Okay, then let us focus on VC of t, that is the next parameter of interest, the voltage across capacitor. Vc of t is equal to 1 by C integral 0 to t, what? I of t into dt. No initial. So then applying Laplace, then we will get Vc of S, that is equal to 1 by C into I of S by S. That's all. That's your Vc of S. So we are interested in Vc of t, means we need Vc of S. I of S available. From this we can play for our Vc of S also. So this is the equation for I of S. Simplify I of S. If we simplify I of S, we'll end up with V in of S divided by taking LCM. It is R, that is SRC plus S square LC plus 1 by S into C you will get. And take SC to the numerator, then you will end up with V in of S into SC divided by this you will get. Getting everyone? Yes. Or in order you can write this as, in order you can write this as S square LC plus SRC plus 1. S square LC plus SRC plus 1 in order. Getting? All of you getting this? Okay, then this is Vc of S. That's our goal. This is going to help us to find I of t. This is going to help us to find Vc of t. So for that, it is 1 by C. I of S is known. Substitute divided by S. I of S by S means the C, this S will get cancelled. So anyway, let me do it formally. So 1 by S into I of S, that is V in of S into SC divided by S square LC plus SRC plus 1. Then this S and S will get in fact SC will get cancelled. So then VC of S, that's a voltage across capacitor, is equal to V in of S by what? A square LC plus SRC plus 1. Or from this, you can also say the transfer function connecting, let me call this as V naught of S. That's output voltage of the circuit. It's taken across the capacitor means I'll take it as V naught of S by V in of S as my transfer function. That is 1 by A square LC plus SRC plus 1. Okay. All of you getting this? Following.
Yes, sir.
So now you can have a system perspective. The system perspective is this. So you have the input voltage to this RLC circuit that is modeled as a transfer function, second order transfer function. Its output is V naught of T. So the system is 1 by S square LC plus SRC plus 1. Okay, I can modify this system by taking LC common. Then I can write this as, or dividing numerator and denominator by LC. We'll end up with 1 by LC, the whole divided by S square plus SRC by LC. SRC by LC becomes what? S into R by L plus 1 by LC. Okay, that's our transfer function, which resembles the standard second order omega n square by a square plus 2 zeta omega ns plus omega n square. We are familiar with this, everyone? Yes. So our RLC circuit is a second order system going to have second order transients. Whereas RC and RL are resembling only what? First order transients. Yes, first time getting into the second order. So we are seeing the second order charging transient of an RLC circuit, where we are interested in voltage across the capacitor first. Okay, yes, what is the voltage V naught of T? Given a step input going from 0 volt to 10 volt or E volt, okay, how V naught of T will respond. Okay, then you can bring all the understanding of second unit of control system, step response of a standard second order system into the play. Okay, step response of standard second order system into the play. That depends on your damping. If damping is between 0 to 1, exploit under damped performance. Damping equal to 1, it's critically damped. Damping greater than 1, it is over damped. Bring all these fundamentals from control system. That's a link between the two topics in control system and electric circuits. Easy? Getting everyone?
Yes, sir.
Okay, now we remember in control system, when a system is excited by input R of T, okay, control system terminology, and the system is K into what? Omega n square. K is the static sensitivity of the system by a square plus 2 zeta omega ns. 1 minute. 2 zeta omega ns plus omega n square. That's your transfer function. And then input is R of T, output is C of T. When the system is excited by a step input, of size A, where R of T is defined as A into U of T, the input applied at time T equal to what? 0 second. Exploiting the step response of the second order system. If it is underdamped, if damping is between 0 and 1, we have the formulation. We don't have formulation for critically damped or over damped. Okay, then we need to go by normal route, partial fraction expansion, and getting into time domain using Laplace transform inverse. That's the only route. So assuming it is underdamped, one can say directly what is C of T? What is C of T? C of T is equal to K is a static sensitivity, A is a step size, then C of T will be AK into 1 minus e power minus zeta omega nt by what? Root of 1 minus zeta square into sine omega dt plus theta. Yes, no other choice. That's the only route. Okay, that's how one can quickly complete our transient using this fundamental step response of second order under damped system. in control system you learned, we are going to exploit this here. Okay, so where A is a step size, K is a static sensitivity. Okay, where omega d is damped frequency of oscillations, that is omega n into root of 1 minus zeta square radian per second. We know that already. And theta is as per the damping triangle cos inverse of zeta. Exploit this. Okay, so bring all these fundamentals which you learned in control system into the RLC second order. Okay, but here the K is equal to 1. So that is resembling K into this. But what is K? Therefore, what is the call? K is equal to K is equal to 1. Static sensitivity is 1. That means the output is going to follow your input at steady state. That's what it means. K is equal to 1 and omega n is equal to omega n square is 1 by LC. Omega n equal to 1 by root LC. And then 2 zeta omega n is equal to the coefficient of S, that is R by L. So from this, damping is equal to R by 2 omega n into L. Substituting omega n as 1 by root LC, then you will get R by 2 into root, that is 1 by LC, and take your L also. L is outside, inside the root if we take, then it is going to become L square, will cancel 1 L. So it is going to become, so if we take this, then it is going to become root L by C. Instead of root L by C in denominator, you can also write it as root what? So it is R by 2 and omega n into L will result in root C by L. Getting everyone? Following? This is already done in control system. Again, we are doing it once again. Okay, as a formality. Okay. So just substitute omega n, you will get this damping. Damping influenced by your R as well as your omega n. So omega n influenced only by the natural frequency of the second order system, influenced by your ln C component, energy storage component. K is a static sensitivity, that is equal to 1. So now taking this fundamental, okay, control system fundamental to this, then input is V in of t and the system is omega n square by a square plus 2 zeta omega ns plus omega n square. That's RLC. Assuming its damping is between 0 and 1, where omega n is equal to 1 by root LC, where zeta is equal to R by 2 into root C by L. This is in radian per second. Damping factor is unitless. So this is excited by a step input as per the given circuit. The system perspective now, this is V in of t. V in of t is equal to the supply voltage, that is 20 or 10. What is taken as supply voltage? 10 volt. Okay. So 10 into U of t you can take, or E into U of t, where E is equal to the battery voltage, that is equal to 10. Let me say E into U of t. That's a input, step input going from 0 to E battery voltage at time t equal to 0 second. Then what's the response across the capacitor means that your V naught of t, that is equal to Vc of t. Okay, is given by, as per the fundamental, V naught is equal to AK into 1 minus e power minus zeta omega nt by root of 1 minus zeta square into sine omega dt plus theta. That's all. Directly can have it into U of t, or t greater than or equal to 0 second. That's your response. Okay, directly we can say, where what is A? Step size. What is that? What is the step size? What is the step size?
E.
E. Okay, replace this by E. And what is K?
Once
1. So replace it by 1. So therefore the output response will be V naught of t equal to E into this transient. If it is underdamped, that's only condition. If it is an underdamped RLC circuit, underdamped second order RLC circuit, underdamped second order RLC circuit, that's your response. Then the response for the given input command is going from 0 to E, then the response will be starting from 0 volt and then will have same response as we discussed in control system. Exponentially decaying transient finally converging to the supply voltage because K is equal to 1 at steady state. Let T equal to infinity in this. Okay, you will get e power minus zeta omega nt into sin omega dt represents exponentially decaying sinusoidal oscillations will die out because of this transient part at approximately 5 by zeta omega n. At 5 by zeta omega n, approximately it will die out, transient part will die out, and V naught of t will approach or converge to a steady state value of E. So this is a time where the response is settling to the final value. That's a minimum time to settle the output response to its final value, 5 by zeta omega n seconds. So this is your transient part, okay, from 0 second to after giving step change. This is how the system is going to react if it is underdamped. And you know very well, if it is critically damped, it is going to be something like this. If it is a critically damped system, it is going to be something like this. If it is over damped, it is going to be even slower. Getting zeta greater than 1, this is zeta equal to 1. We know that I'm taking all this fundamental from control system only so that the conclusions are easier. So this is zeta less than 1 but greater than 0 under damped system. Okay, so bring all the fundamentals of second order control system excited by step input into the RLC transients. Charging transient. It is charging from 0 to E, okay, with transient oscillations. Decaying transient oscillations. That's how we can conclude instantly. Getting? All of you getting this? Yes or no?
Yes, sir.
Then after getting V naught, you can get your current. Okay, you can easily get your current. Otherwise, okay, you can also get the current directly by using this equation. Okay, from this also you can get the current easily. Okay, so that is going to resemble unit impulse response of a second order, but we can do it once. So we know I of S is equal to V in of S into S into C divided by A square LC plus SRC plus 1. I'm talking about the current. So this current is the current through the capacitor as well. I can evaluate this as I of t equal to current through the capacitor. We know that's I and this is V. The connection is I is equal to C into dV by dt. I know the voltage across capacitor. So I can find the current by doing C into differentiation of what? V naught of t. Okay, this is one way. Since V naught of t already available, okay, V naught of t already available, you can differentiate it, but that is going to involve a differentiation of e power minus zeta and sin omega dt. That's one route. Okay, another route is assuming problem is only looking for the current, then you need not to find out your voltage. But remembering that equation is very easy comparing to your I of t. But still, let us go for I of t because the goal is to get two responses. One is output voltage V naught that is across capacitor. Another one is current through the entire circuit. Okay. So let us get I of t from this. That's a goal. Yes, substitute V in of S. V in of S is equal to what? V in of t we know that is equal to E into U of t. That's a battery voltage into this. Then it is going to become E by S. Substitute that. Then you will get I of S is equal to V in of S is E by S into S into C divided by A square LC plus SRC plus 1. Okay, then S and S will get cancelled. So then you can also take divide numerator and denominator by LC. You can say I of S equal to dividing by LC. S is getting cancelled, dividing by LC. What is the remaining in the numerator? What is the remaining in the numerator? E into C, right? So keep the E into C common and then numerator divide by LC, denominator also divide by LC, then S square plus S into what? R by L into, sorry, plus 1 by LC. This is your standard second order. Then I can say this is I of S is equal to Eec into omega n square by A square plus 2 zeta omega ns plus omega n square. That's your I of s. Okay, from this you can find I of t. So I of s is equal to E into c into omega n square by s plus zeta omega n whole square plus omega d square. We know very well a second order system under damped is going to have zeta between 0 and 1 will have real part minus zeta omega n, imaginary plus j omega d, and this is minus j omega d. Exploit these fundamentals, then writing it in the form of so s square plus 2 zeta omega ns plus omega n square can be written as this. Okay, getting everyone? Yes.
Yes.
Then we remember the identity Laplace of e power minus at into sine omega t is going to be omega by s plus a the whole square plus omega square. That's a purpose. I need to make this in this form of Laplace identity. Now let us find I of t after modifying this. So multiply the numerator by omega d and divide by omega d. Small adjustment. Then you will get I of t. So then I of t is equal to Ec divided by Ec into omega n square divided by omega d. You will get rest is applied Laplace inverse, that is e power minus zeta omega nt into sine omega dt. Okay, getting everyone? That's your current I of t is equal to omega d, you know. So there is omega n into root of 1 minus zeta square. Replace it. This is omega n into root of 1 minus zeta square. This omega n will get cancelled. Then as a result, e into c into omega n divided by root of 1 minus zeta square into e power minus zeta omega nt into sine omega dt into u of t, we can say. Okay, that's your current. All of you getting this? Following?
Yes.
Okay, yes. Take the two equations. One is the current I of t that is equal to Ec into omega n by root of 1 minus zeta square into e power minus zeta omega nt into sine omega dt plus t. Sorry, omega dt only, no theta. Here into u of t, we can say. That's I of t. Voltage V naught of t, that's voltage across capacitor. That is E into 1 minus e power minus zeta omega nt by root of 1 minus zeta square into sine omega dt plus theta. Okay, into u of t. That's all. If you plot the two responses, already we know I of t will be like this and V naught of t will be like this. Under damped case, with respect to time, I of t will be starting from 0, then we'll have exponentially decaying oscillations, then the response will look like this. That's your I of t starting from 0 current going to end at 0 current. Yes. So the current through the inductor or entire circuit is 0 initially, finally also 0. We'll see why. Then V naught of t begins with 0, but it is exponentially growing and oscillating around the final value and settling at the battery voltage E after 5 by zeta omega n time. Here also after 5 by zeta omega n time, it is approximately settling to steady state value. That's how we get transient current response and transient voltage response, provided it's a underdamped system. If it is critically damped or over damped, we have to start from the scratch and then get the responses. Is it clear, everyone? Yes. Following, right?
Yes, sir.
Let us see what happens in the circuit. Okay. So that's understanding as a system perspective. The circuit treated as a system, second order under damped system. Then we got the responses. Then as a circuit, we'll see what is the perception. So feel like this. That's a switch getting closed for t greater than or equal to 0 seconds. Excited by a battery of 20 volts, for example. I have a resistor of 5 ohms, inductor, and capacitor. Let us play with the numbers. Let me fix omega n, accordingly choose L and C. Omega n, let me say it is 10 radian per second. Omega n is 10 radian per second. So omega n is equal to 1 by root LC. So fix it. So what is root LC? Root LC equal to 1 by 10. Correct? Getting everyone? Following, right?
Yes, sir.
Root LC equal to 1 by 10. Then LC equal to 1 by. Getting square both sides. Okay, omega n square. LC equal to omega n square. That's all. 1 by LC equal to omega n square. So LC equal to 1 by omega n square. So it's 1 by 100. That is nothing but 0.01. So let us fix LC 0.01. So accordingly, fix the value of L. For example, L is equal to C is equal to 10 farad. L is equal to total should be 0.01, right? Okay. So then 1 millihenry. Tell me what is the product LC now? L is 1 millihenry. C is 10 farad. What is the product LC? 10 power minus 3 into 10. So it is going to be 0.01 met this condition. Okay, that's my circuit consisting of resistor of 5 ohms, inductor of 1 millihenry, and capacitor of 10 farad. Okay, fine. So the calculations are shown only for the understanding. Take this way now. Okay, it's a design. That's all. Now let us play with the circuit. Okay, assuming someone makes such a design by playing with these numbers and giving as RLC circuit consisting of resistor of 5 ohm, inductor of 1 millihenry, and capacitor of 10 farad. Okay. Now, at time t equal to 0, 0 minus, we don't have any initial conditions. So time t equal to 0 plus. Let us begin the analysis at time t equal to 0 plus. So this is the current I of t and this is the voltage V naught of t. Okay, taken this way. Okay, so we know I of 0 minus is equal to what? 0 amps. We also know V naught of 0 minus is equal to 0 volt. That's a voltage across capacitor. This is a current through the inductor. We don't have initial conditions. Initial energies associated with the inductor and capacitor. So at time t equal to 0 plus, what happens? And we know the fundamental at time t equal to 0 plus. Whatever your current through the inductor, that won't change. That means I of 0 plus will follow I of 0 minus because inductor won't allow change in current. That is the reason This is beginning with 0 amps even at time t equal to 0 seconds. Getting everyone? At time t equal to 0 second, even after applying the input, the current is not having a change. It is still 0 only. So that means it is 0 minus or 0 plus. The current will remain 0. That's the reason. Getting everyone? Getting everyone?
Yes, sir.
And similarly, we know V naught of 0 plus is equal to V naught of 0 minus. That's a capacitor voltage. And initial voltage is 0. Therefore, even after switching your input supply, capacitor voltage won't change. Capacitor cannot change, cannot allow instant change in voltage. Inductor cannot allow instant change in current, understanding the property of both these elements, both elements. You see? You see, right?
Yes,
So
sir.
the reason why the output voltage begins with 0. Okay, at 0 second. So the output voltage 0 minus or 0 plus, the voltage will remain what? 0. So it is beginning with 0. For current is beginning with 0 minus, that is 0, and 0 plus also 0. Voltage is similarly 0 minus, it is 0 volt. 0 plus also it is 0 volt. That's a response. Okay, let us play at time t equal to 0. Then current in the circuit at time t equal to 0 plus is 0. That's a quick understanding. Current is 0, no current in the circuit, and no voltage across capacitor. That means this voltage is equal to what? Taking this as a reference, then this point potential is 0 volt. Okay, and no current means what's a drop across your resistor? What's the drop across resistor?
0 volt.
0 volt. That's what happens in the circuit. Yes, you should not simply go ahead and conclude with a system perception. You should know what is really happening in the circuit at time t equal to 0 plus. So time t equal to 0 plus, no current exists in the circuit because inductor won't allow change in current. Therefore, the voltage across resistor becomes 0. So, and KVL is there. Vn is equal to voltage across resistor plus voltage across inductor plus voltage across capacitor. At time t equal to 0 plus, interestingly, no voltage across resistor, no voltage across capacitor. And inductor shows full opposition for the change in current by taking entire supply voltage across it. That's what happens. So now this is 0 means this point is 20 and you are not getting anything across the resistor. Therefore, this point is still 20 volt and capacitor is not holding any potential. Therefore, this point is 0. Therefore, voltage across inductor is going to be the entire supply voltage. Getting everyone? Yes or no? Yes or no?
Yes,
What
sir.
is the understanding? VL of 0 minus is equal to 0 volt, but VL of 0 plus is equal to how much? 20 volts. Getting? All of you getting this? Yes or no?
Yes, sir.
So the inductor begins with 20 volts at time t equal to 0 plus. That's a circuit perception at time t equal to 0 plus. Anyone having doubts? Anyone having doubts? Okay, then we'll play at time t equal to infinity. At time t equal to infinity. Inductor, okay, doesn't have any change in current. That means inductor at steady state will act as a short. No voltage across inductor. Capacitor at steady state will have zero current. Getting everyone? All of you getting? That's all we know. Inductor at steady state will have no voltage. Capacitor at steady state will have no current. Then begin the analysis. This is 0 volt. This is 20 volt. Again, therefore this point, so just closed. This is 20. And no current again. Current is 0. Current is again 0. That means what is the voltage here? 0 volt. Okay. So therefore this point is 20. But interestingly, voltage across inductor is also 0. Then what is this point then?
20.
20. Yes. Now where? What is the voltage across your capacitor? The bottom is 0. Top is 20. What is the net voltage?
20 volt.
Yes, the capacitor fully charges. So VL of infinity equal to 0 volt, whereas VC of infinity equal to the full voltage applied, whereas the current VR of infinity also equal to what? 0 volt. And current at time t equal to infinity also equal to what? 0 amps. That's all. So the capacitor fully charges to your excitation. Yes, still it is fully charges to excitation. So Vc of infinity is 20, whereas Vc of 0 is equal to what? 0. That is Vc of 0 only. Okay, that is 0. That's your V naught. Here also you should have taken as V naught only. Okay, instead of Vc. Vc of infinity, nothing but V naught of infinity. Getting everyone? Getting everyone? Yes.
Yes, sir.
And the waveform is confirming that the current is beginning with 0, ending with 0. Okay, but in between it is having transient oscillations. Reason, the voltage across the capacitor will change, okay, sinusoidally. So the circuit has to obey the KVL. Current exists, okay, during transient. Current exists during transient. Okay, voltage will experience, because this voltage across capacitor will experience sinusoidal decaying oscillations. Finally it will reach your supply voltage, that is E, but in this case E is equal to what? 20 volt. That's a waveform your V naught is going to follow. Is it clear, everyone? Is it clear?
Yes, sir.
So anytime you can find the voltage across capacitor, with that you can also find the current at any time. Okay. So now let us play with these values for the current and voltage. We'll see how to answer a problem set in transient. Okay. So you know your current I of t, you know your voltage Vc of t, that is V naught of t. Yes. And omega n for the circuit, please. Omega n, any t, answer for any t. Omega n 1 by root LC. Okay, what is omega n? Yes, substitute the values, you'll get the answer as 10 radian per second. Already we decided. Okay, design the circuit for this only, because the product L and C is equal to 0.01. Therefore, 1 by root of 0.1 become 1 by 0.1, that is 10. And zeta, please. Zeta, please. R by 2 into root C by L. Okay, check whether it is a underdamped system or not. Check whether it is 100 damp system or not. Find out zeta. Zeta is equal to R is 5 ohm and by 2 root of, I'm not sure. If it is not 100 damp, we'll make it 100 damp by changing R. C is 10 farad. L is 1 millihenry. So that means the damping is too large, correct? Yes or no?
Yes, sir.
Too large. Okay, so now let me make a small change. But anyway, so far t equal to 0 plus t equal to infinity doesn't exploit the values of L and C. That's all. Independent of L and C, this is your time t equal to 0 plus situation. Independent of RLC, this is your time t equal to infinity situation. Let me make it under damped. Okay, to make it under damped, let me change my omega n. L is equal to 1 Henry, C is equal to 1 farad. Okay, what you will get? Okay, root C by L. So let L is more. L is equal to 10 Henry. C is equal to 1 farad. Okay, 1 by 10 you will get. So make it 0.1 farad then. C is equal to 0.1. 0.1 won't help. 0.1 by 10. Okay, will help. 0.1, 1 by 10, 1 by 10. 1 by 10 and 10, it is going to be 100. Okay, so then R by 20 will get, that's fine then. Okay, let me use this L. A small change. L is changed. It is 10 Henry. C is going to be zero point 0.1 farad. That's a change in data. Yes, now tell me what is omega n. And this omega n, please now. That's a new system. Yes. 1 by root of L and C product 10 into 0.1. That is going to be 1, right? Yes. So it is going to be 1 radian per second. So omega D is, sorry, omega N is 1 radian per second. Here zeta, please. Zeta, please. R is 5 ohms divided by 2 into root C by L. That is 0.1 divided by 10. So then zeta becomes, intention is to make it 100 damped. So 5 by 2 into root of 1 by 100. So zeta is going to become 5 by 20. 5 by 20 means 0.25. Getting everyone? Yes? Yes or no?
Sir.
So zeta is saying clearly the given second order is underdamped. Then we can play with our underdamped responses. Otherwise we can't play. Okay, so you need to check always your damping. Then you have to decide, okay, whether you have to play with the previous formulation or you need to start from the scratch. If it is critically damped, you need to start from the scratch. If it is over damped, you need to start from the scratch. Only if it is under damped, you can use this formulation. Okay, right? Yes, what is I of t? I of t. If you remember, I of t Eeci into omega n by root of 1 minus eta square into e power minus zeta omega nt into sine omega dt into u of t. That's your current in the circuit. Let us go for the current where E is the battery voltage. That is equal to 20. Yes, tell me what is the current now substituting. You know your zeta, you know your omega n. You can find out your omega d only, where omega d is omega n into root of 1 minus zeta square. So root of 1 minus zeta square is 1 minus 0.25 square. 1 minus 0.25 square, please. That's your omega d. Omega d, please. Otherwise, I will do one thing. I will make a round number for this also. So it's a 0.25 instead of 0.25. Let me choose this as a 4 ohm resistor. So this is going to be 4 ohm and this is going to be 4 by 2. Then it is going to be 4 by 20. 4 by 20? 1 by 5? 1 by 5 is
Into
0.2. Yes, it's easy calculation now. If it is 0.2 instead of 0.25 square, it is 0.2 square. Will help. Okay. Yes. 0.2 square is 0.04. Then omega d is going to be root of 0.96. Okay, radian per second. Getting everyone? Yes. Okay. All of you
yes.
getting?
Yes, sir.
Then the current I of t is going to follow this. E is 20 and the capacitor is what? 0.1. So 20 into 0.1, take that as a magnitude. So this is going to be your magnitude. This is your magnitude. Remember, calculate your magnitude. .20 volt into 0.1 omega n is 1 divided by root of 1 minus zeta square. That is same as this omega d because omega n is 1. So by root of 0.96 into e power minus zeta omega n. Zeta omega n is zeta is 0.2. Omega n is 1. So e power minus 0.2 t into sine omega dt. That is sine of root 0.96 times t. That's all. All of you getting? All of you getting?
Yes, sir.
So then I of t. Tell me what is this magnitude, please. This magnitude, please. That's your current magnitude. 20 into 0.1, 2. 2 by root of 0.96. 2 by root of 0.96.
2.041.
2.041. So this is our I of t and this is our Vc of t. I of t is 2.01.
041, sir.
041, no?
Yes, sir.
041 into e power minus 0.2t, e power minus 0.2t into sine root 0.96t into u of t amps, we can say amps. That's all. Okay, now time t equal to 0, you will get 0 only. Time t equal to infinity, you will get that 0 only. Okay, now substitute t is equal to, for example, so settling is going to be phi by zeta omega n. It is going to settle at phi by zeta omega n. That is nothing but phi by zeta is zeta is zero point 0.2 and this is omega n is 1. So 5 by zero point 0.2 seconds approximately. That's where it is going to settle. That means it is going to settle approximately at 25 seconds. So if you want to set any transient, set within this period. So find out I of 5 seconds. That's really a transient. And I of, for example, if I say 50 seconds, that is equal to I of infinity and current will be equal to 0. Getting everyone? Because it is at steady state. Following? Following, right?
Yes, sir.
Yes, find out I of 5 seconds. That's a current at 5 seconds. So we'll see what happens in the circuit at time t equal to 5 seconds. At time t equal to 5 seconds, we'll see what happens in the circuit. Find out the current I of 5 seconds. That is 2.041 into e to the power of. Can anyone tell me what is this time? The current is maximum. Current is maximum means
Peak time.
that actually we are playing with the I of t, not V naught of t. This is the peak time. Getting everyone? Yes or no? This is the peak time. Again, in that case, you can play with pi by omega d. That's a peak time. Here, it's not peak time. Okay, it's a peak time for the current, but that is not the peak time of this response, second order response. We can't use pi by omega d for the current. Okay, maybe you can play at pi by omega d for this. Okay, so that will be the maximum voltage across your capacitor. Okay, all of you getting?
Yes, sir.
Following, right? Yes.
Yes, sir.
Yes, now substitute your t equal to 5 seconds. Get e power minus 1. T equal to 5 seconds, you will get e power minus 1 sine root 0.96 into t is 5 seconds. Yes. Get your answer. One minute, I'll be back. Yes, what's the solution?
0.064. 0.064.
0.064. Okay. Anyone can confirm the same?
Yes, sir. Same answer. 0.0641.
0.0641, sir.
Okay. I have a small doubt in that. Okay, let me confirm.
Sir,
Yes.
shouldn't we do like 180 divided by pi, sir,
Yes,
in
you
that
have to.
sign?
Yes, you have to. So 2.041 into e power minus 1 into sine of root of, it is in radians. Tejal, it is in radians. Fadil, it is in radians because it is root 0.96 is radian per second and this is second. So it is going to be in radians directly. Don't do sine. Okay, convert that into degrees. Okay, yes, that's a caution.
So then,
So 5, yes, 5 into, let me do it once. Sine of 5 into root of 0.96. That is in radians, so 180 degree by pi, or directly keeping the calculator in radian more, you can get the correct answer. The mode is very important. Yes, tell me now, same answer Tejal or different? Yes, Yashwant.
minus 0.7373.
Minus 0.7373. Yeah.
Yes, sir.
Yes, Tejal. Fadil, please confirm.
Yes, sir.
Yes, that means the current is here. Yes, it's in its negative cycle. Possible, right? Never get surprised by seeing negative current. It is possible. It can have positive as well as negative cycles. Sinusoidal oscillations. Getting? That's the purpose of this example. Okay, finding the current. Okay, then once again, let me go ahead with the circuit at this point of time. Understand what really happens in the circuit now. Yes, now the current is negative. The current is negative means how we took the current direction? We took the current in this direction. That's what our I of t is. Current is negative means what is the right direction now? Tell me what is the right direction of current? What is the right direction of current in the circuit?
Oppositely, right, left.
Opposite. Yes, right to left. What is that current magnitude? You know it is 0.73 or approximately 0.74. Let me take approximately 0.74. Let us play with 0.74. It's minus 0.74 amps. Taking this, the current is 0.74 amps. Okay. So now tell me what's the voltage across your resistor. That is negative actually. We should take this as plus, this is current is negative, voltage is negative, but I'm going for the actual voltage. Okay. What is this voltage? Into 5. 0.74 into 5 approximately.
3.7.
3.7 volts. Now tell me what is this point potential? Taking this as 0. Taking this as 0, this is 20. And 20 plus 0.7? Sorry, 20 plus 3.7. 23.7 volt here at this point. Okay, getting?
Yes, sir.
Okay, we don't know what is the voltage across inductor. We don't know what is the voltage across capacitor. We'll find voltage across capacitor at the same time. We know we need to find out VC at what? 5 seconds. We'll see. VC at 5 seconds is VC of t. We know that is equal to S. VC of t is E into 1 minus e power minus zeta omega nt by root of 1 minus zeta square into sine omega dt plus theta into u of t. Omega d we know, theta alone is unknown. Cos inverse of zeta, please. Cos inverse of 0.2 since zeta equal to 0.2. Is cos inverse of 0.2?
78.46.
Okay, degrees. Use that. Okay, then VC of t, VC of 5 seconds is equal to E is how much? 20 volts. So 20 volts into 1 minus e to the power of zeta omega n is already known. Zeta is 0.2, omega n is 1, omega d is root 0.96. Exploit e power minus t divided by root of 1 minus zeta square, also going to be root of 0.96 only. Then into sine omega d is root 0.96 t. Okay, plus theta, that is 78.46 degrees. Play carefully here. Okay, when you substitute your time, this is at time t equal to t. This is VC of t. Yes, now let t equal to 5 seconds, then VC of 5 seconds is equal to, any mistake committed? Zeta omega n is
0.2, sir.
0.2 t. Okay, then 20 volt into 1 minus e power minus 1 by root of 0.96 into sine, and root of 0.960 will have the same value as the previous one. Tell me what is this angle? Tell me what is this angle? 5 into root 0.96 into 180 by pi. Give me that angle. That will be this. Add with that angle 78.46. His total angle, please. Sine of, what is the angle in degrees?
Minus 0.9826, sir.
Yes.
Minus
Minus. Why
0.9826.
minus? Why minus? 5 into root 0.96 into, you're talking about the answer, Fadil? Okay, I'm asking about the angle. It is 5 into root 0.96 into 180 by pi. Getting? So tell me what is the total angle, anyone? Including the 78.46. You are substituting 5. So it is root 0.96 into 5 multiplied by 180 by pi. Convert that into degrees, add with 78.46. Then you have the result. What is that number? Angle, please. Sine of what angle?
359.35.
359.35
35.
degrees. Okay. Almost sine 0, right? Yes or no?
Yes, sir.
Okay. Tell me what is the exact value of VC at 5 seconds? It's not going to be 0. That value will exist. So find out VC of 5 seconds. Just calculate.
$20.11.
20.11. Next digit, Tejal.
1, sir.
Okay, 20.11 volt is the voltage across your capacitor at this point of time. So then yes, take that voltage across your capacitor. So voltage across capacitor is known. That is 20.11 volt. Okay, yes, that's all we can say. This is 23.7. Tell me what is the voltage across your inductor then. This is known as 20.11 because the bottom is 0. It's 20.11. This is 23.7. Okay. So then differences, this is higher potential, this is lower potential, that is your VL. So VC is positive, VL is also positive, but VR is going to be negative. VR is should be taken this as plus and minus. Yes, VL please. What is the VL remaining? 23.7 minus 20.11.
3.63
3.63 volt. But not to forget that your circuit has to obey the KVL. Vn equal to VR plus VL plus VC. Roughly verify. Okay, that's VC. Roughly verify. But the left hand side 20. Right hand side VR will be minus of this drop. So it has to be taken as minus 3.7 volt. Okay, plus VL we got as 3.63, that is positive, and plus your voltage across capacitor, that is also positive 20.11. Anytime the circuit will maintain the balance. Tell me what is the right hand side? Balanced. Right hand side should be equal to 20. Are you getting 20 or something closer to that?
Sir,
Yes.
sir, we have taken resistance equal to 4 ohms, not 5.
Okay. So resistor equal to
4 ohms.
okay. 1 minute. Okay. Then it has to be different. It has to be 4. Then tell me what is the voltage for this? Yes, correct. It's not 3.7. It has to be 4 into point. Yes, tell me what is that drop? Not 5 into 4 into 0.734 or 4 into 0.74.
4 into points on first 2.96.
2.96. Okay, that's fine. Then it is not going to be 23.7. It is going to be 22.96 volt. Then we are getting this potential. Okay, 20.11. So this is different. Okay, 1 minute. Yes, the voltage across the capacitor is 20.11. So this is 20.11. Okay. Plus minus. So therefore, this is going to be 20.11. Yes, voltage across inductor, please. 22.96 minus 20.11 will be the voltage across inductor.
2.85.
2.85 volt. Now verify supply voltage. Vn 20 volt is equal to voltage across resistor is minus 2.96. Taking this as plus and minus, that's your VR as per the circuit analysis. Plus voltage across inductor is positive, that is 2.85. Plus voltage across your capacitor 20.11. Hope it is balanced. Hope it is balanced.
Yes, sir.
In fact, I should not, I am finding VR from the current. I'm finding VR from the current. I'm finding VC from the voltage. That's fine. But finding VL, not directly. Okay, finding VL only by using these two, definitely the equation will get balanced. Okay, it did manipulation. If you want to correctly find VL, then you have to find VL using L into di by dt. So you need to differentiate your I with respect to time and use that data at this point of time. So you need to find out dA by dt. You need to find out dA by dt at what? 5 seconds. Then find out the voltage that will match 2.85. Then this is perfectly all right. All of you getting? All of you getting this? Following?
Yes, sir.
So never get surprised. Even by giving 20 volt, this is plus and minus. If the current direction is given this way at some point of time, that is possible because the current is going to have this pattern of waveform. Correct? That's your profile, current profile. Starting from 0, ending from 0. In between, it may have positive off cycles or negative off cycles. Current may be positive or negative. Understood? Is it clear? Yes.
Sir, and inductance is 10 Henry, so not 1 millihenry.
Inductance?
10 Henry.
Fine. Anyway, that we didn't take those values now for the calculation. For the okay. Getting? Because we didn't use 10 farad and 1 millihenry. Not a problem. We have just L and C. Okay. But resistor we used in the calculation, so it can be changed. Getting? All of you getting this point? Yes or no? LNC values included in our omega n and omega d. Okay, so that we didn't change. So responses won't change because of them. Getting further?
Yes, sir.
Okay, yes. Only the response will changes. The one which is exploiting the resistance value. So resistance is 4, therefore it can change. Hope it is clear, everyone.
Yes, sir.
Okay, yes. So that's how a capacitor charges the second order transient. Okay. Now the above capacitor charge up to what? The above capacitor charged up to what? Up to the supply voltage it will charge. Now let me show this arrangement. This is going to talk about RLC discharging transient. That's a position A. It's position B. 20 volt battery. Resistor of 4 ohms. Inductor, please. What are the inductance we used? What are the inductance we used? Last example. L is equal to what is the L we used? 10 Henry. C we used 0.1 Farad. So it is 10 Henry and this is 0.1 Farad. That's all. That has given omega n is equal to 1 radian per second natural frequency and zeta is equal to 0.2 in the given circuit. Yes, then. Situation is this. The switch is connected to position A for a long time. Okay, and then thrown to position B for t greater than or equal to 0 seconds. Okay. Tell me what is Vz of 0 minus. That's your switch. Switch is in position A for a long time and is thrown from A to B at time t equal to 0. Switch connected to A for what period? For t between minus infinity to minus 0. Switch is connected to position B for what? T greater than or equal to 0 second for clarity. Getting everyone? Following this?
Yes.
Now what will happen at time t equal to 0 plus? At time t equal to 0 minus, what will happen first? 0 minus. At time t equal to 0 minus, initial steady state. Initial steady state, this is 20 volt. The current in the circuit will become 0. Then voltage across the resistor will be 0. And voltage across inductor also going to become 0 because at steady state. And therefore entire voltage will be with the capacitor, that is equal to 20. Capacitor is fully charged and holding an energy of CV square. Holding an energy of CV square that is going to release its energy to begin the discharging transients. Okay. When it is going to discharge? When the capacitor, so when the switch is connected to position. When the switch is connected to position B. Getting everyone? Yes or no? Following, right?
Yes, sir.
So now the switch is connected where? To the position A. That's a connection. Will connect it to B. Okay. In the next circuit will begin discharging transient. Okay. So for t greater than 0, this is what happens. T greater than 0 second. T greater than 0 second. It's connected to the short. So therefore the circuit is this. It's your resistor. 1 minute. inductor and capacitor. That's your equivalent circuit. The capacitor is initially charged up to 20 volt. Inductor is 0.10 Henry, 4 ohms. This is 0.1 farad. Values are given. That's your switch position now. Here's for time t greater than or equal to 0 plus. And we know the current through the inductor is 0. Vc of 0 plus will be equal to Vc of 0 minus, that will be equal to what? 20 volts. Okay. And similarly, the current in the circuit now, in what direction you need to put the current now? Tell me in what direction you need to put the current now. T for greater than 0 second. T greater than 0 seconds. What direction we need to put the current now? Take this as a reference. Okay, 0 volt. This will be how much? 20 volt. Then the capacitor is acting as a battery of 20 volt. Therefore, it is going to deliver the current in this direction. That's a correct direction marking. That's a discharge current. Able to follow me? That is a one going to discharge your capacitor. Let me take the discharge current direction. Capacitor is about to discharge. So current is going to, why discharge? Because the discharge current is going to feel like discharge current is charging the capacitor. This is plus and minus. So this is a new charge, this is a old charge. The net charge will be less. This is the old charge and this is the new charge. So therefore the net charge will be less. So it is decreasing. Okay, so that's a discharge current. So the current is in this direction. So that current is still 0 because earlier you know that 0 minus inductor current is what? In this direction, that is 0. It won't allow the change in current direction also. So the magnitude itself is going to be 0. So the current is 0 at time t equal to 0 plus. At time t equal to 0 plus, the current is going to be 0. This voltage is 20. This is 20 and this current is going to be 0. Okay. Here's then. Is the point clear, everyone? Yes or no?
Yes.
All of you getting? If that is the case, where the voltage is going to fall? If that is the case, where the voltage is going to fall? I say current is 0, right? Current is 0 means where the voltage is going to fall. Current is 0 means what's voltage across a resistor?
Zeros.
0. Then where the voltage is falling?
Plus
Across your
capacitor.
inductor. Across your inductor. This is plus minus. What is the voltage across inductor? 20 volt is the voltage across inductor. The entire 20 volt is falling across your inductor. Reason inductor shows full opposition for the change in current. Okay, it won't allow instant change in current. Then slowly it will release opposition. So the voltage will decrease. Then it will allow a voltage across the resistor. Then the current will increase. Once there is a current, capacitor will start discharging. If no current, capacitor won't discharge. Understood? Since we have a resistive element in the circuit, that's energy dissipating element, therefore we are going to lose energy in the circuit. So that's one beginning discharging transients in the circuit. Is it clear? Yes or no?
Yes, sir.
So now let us find the discharging current and the expression for the Vc of t as well. Okay, the goal is this. So we need to find Vc of t expression, assuming it has the initial voltage Vc of 0. And find the current I of t in this direction. That's what we need to find for t greater than or equal to 0 seconds. Okay, we'll do that. So make a KVL with respect to this. So it's equivalent circuit for t greater than or equal to 0 seconds. The circuit is this. What we have is a resistor, we have inductor, and we have a charged capacitor. That's all. That's your equivalent. Capacitor with a charged voltage. This is Vc of 0. Okay. 0 minus or 0 plus, that is shortly 0. Then we are going to find Vc of t. That is Vc of t in the same potential marking plus and minus. Even though the current is discharging current, that is I of t. The goal is to find the current response, discharging current I of t and the discharging voltage Vc of t. You can also find any other response if necessary. You can find Vr of t. You can also find VL of t in the circuit. Okay. So anyway, this is a fundamental. Vr of t is equal to R into I of t. Once I is known, we can find this. Then VL of t is VL of t is VL of t is L into di of t by dt, we can say. Or you can also exploit this equation as per the current direction. As per the current direction, yes, this is the voltage VL and this is the voltage VR as per the current direction in the given circuit. Now tell me what's a KVL in this circuit. What is the KVL in the circuit? Yes, what is a KVL? Current is entering here. So therefore VL of t. Current is entering here. So plus VR of t. And that's a current coming here. That is entering here. But entering what? Minus terminal of your VC. So minus VC of t equal to 0. That's our KVL. Getting everyone? All of you getting this point? Yes or no? Following, right?
Yes, sir.
Then at any time VL of t plus VR of t will be equal to voltage across your capacitor. That's acting as a source. That's what it means. So VC is supplying, VL and VR are taking. That's a KVL. Quickly one can write. So see from this, that's a supply. Treat the voltage across capacitor as a supply, and this is taking. This is taking. So therefore, these are the drops. Therefore, VC equal to VL plus VR. One can say directly. Okay. So from this also one can find VL of t. You need not to differentiate your I and multiply by L. From this one can say VL of t anytime is equal to VC of t minus VR of t. One can say this. So the point is, if you know the current I, if you know the voltage V, then you can find this as well as you can find this anytime. So this is an easy equation. Unnecessarily don't differentiate your current and complicate. Simply go for VL of t. Yes, VC of t available. So VR of t available. Do the simple subtraction instead of differentiation. Differentiation is time consuming comparing to this simple subtraction. So this is a better route for VL of t. Hope it is clear, everyone. Hope it is clear. Yes or no?
Yes, sir.
Yes, sir.
So the goal is to find the discharging transient current and voltage.
Sir,
Yes.
sir, we have considered that VC of 0 minus and 0 plus equal 20. So why didn't you substitute equal 20 volts?
Now you're asking, Fadil? Now you want to substitute 20?
Sir, we have found so.
No, anyway, VC of t will include that VC of 0.
Okay, sir.
Okay, we'll see where the VC of 0 coming into play. Okay, we'll see that, Fadil. Okay. Yes, begin the analysis now. So VC of t is equal to VL of t plus VR of t. That's our KVL. Playing with respect to the current now. So playing with respect to the current. So tell me, what is this VC of t? What is VC of t now? So this is your voltage. This is the direction of the current I of t. This is the voltage VC of 0. And this is also the voltage VC of t. This is C. Tell me what is VC of t now? It is holding the initial voltage. Okay. What is VC of t? If I have an initial voltage like this, initial voltage is VC of 0. And if I have a current like this, that's I of t. Then I can say VC of t like this. What is the VC of t for this? VC of t for this is minus infinity 1 by C into minus infinity to t, what? I of t into dt. Then I will write this as VC of t equal to what? 1 by C integral minus infinity to t I of 0, I of t into, sorry, till 0 dt plus 1 by C integral 0 to t I of t into dt. So someone charged my capacitor in the same direction how I is also charging. I is the current in the capacitor charging this as plus and minus. That extra charge is this. And this is my early charge. Okay. That is VC of 0. So in this case, what happens is VC of 0 and the present charging are in the same direction. So it is aiding. Therefore, I can write the equation as this one. So here, tell me what to write. Tell me what to write here. For this situation, it is the equation. For this situation, what is the equation? And I of t is going to charge the capacitor. This is plus and this is minus. Therefore, the new charge is opposite to the old charge. Therefore, VC of t should be written as what? VC of t should be written as. I am writing the polarity marking this plus minus. So VC of 0 in the same direction. So put minus 1 by C integral 0 to t I of t into dt. Getting everyone? Getting this? Following, right? Yes or no? Following or not?
Following, sir.
Yes, that's all. That's only change. Clear, Fadil? Getting Fadil?
Yes, sir.
Yes, now you can make your KVL. Therefore, your VC of t is equal to VL of t plus VR of t is going to become your VC of 0 minus 1 by C integral 0 to t I of t into dt is equal to L into di by dt. That's a discharging current plus R into I of t. Apply Laplace. Applying Laplace. What do you get then? VC of 0 by S minus 1 by C into I of S by S equal to L into S into I of S minus I of 0 but no initial current plus R into I of S. Then VC of 0 by S. VC of 0 by S is equal to 1 by SC into I of S plus SL into I of S plus R into I of S. You will get, take I of S common. Then you will end up with 1 by SC, SL plus R. Hope it is clear, everyone. Yes? Following,
Yes,
right?
sir. Yes.
Then the next equation will become VC of 0, that's initial voltage, divided by VC of 0 by S. That is equal to, right hand side, I of S can be taken as common. Then you will get SL plus R plus 1 by FC. Take this way, then take LCM. Then I of S into, you'll get A square LC plus SRC plus 1 by S into C. You will get this VC of 0 by S. So this S will get cancelled. So then C into VC of 0 will be your I of S into A square LC plus SRC plus 1. Getting everyone? All of you getting? Yes or no?
Yes, sir.
So then I of S will be equal to C into VC of 0. That's initial voltage divided by A square LC plus SRC plus 1 can be written as taking LC out. So LC out resulting in C by LC VC of 0 by A square plus S into R by L plus 1 by LC. Don't discard this 1 by LC, but you take it as 1 by LC. Okay. So that it will resemble your second order. Okay. 1 by LC. That's better way. So that's your I of S. So better you can write this as C into VC of 0. That's a constant. So C into VC of 0 into this second order term. Okay, so I of S resembles C into VC of 0 into omega n square by A square plus 2 zeta omega ns plus omega n square. Getting everyone? Is that okay? Following? Following, right?
Yes, sir. Following.
Then I of S is equal to C into VC of 0 into omega n square by omega d into omega d divided by S plus zeta omega n whole square plus omega d square. That's a modification. Then get I of t. Okay, ready for Laplace inverse. Omega d can be replaced by omega n into root of 1 minus zeta square again. Omega n will get cancelled. Then C into VC of 0 divided by root omega n. Okay, so okay, take this as common. That's a charge, initial charge. Okay, C into V, it's a charge. C into VC of 0 is a charge into omega n by root of 1 minus zeta square into Laplace inverse of this will be e power minus zeta omega nt into sine omega dt. That will be the discharging current in the capacitor in the RLC second order circuit. Getting everyone? Following? Yes or no? Following, right?
Yes, sir.
Then get your VR of t. VR of t. Ultimately, the goal is VC of t, right? We can find VC of t. How to find VC of t? Yes, we need to find two parameters. One is I of t, another one is VC of t. Yes, what is VC of t now? How to get VC of t? Do you want to integrate the current and do it, or quickly find VR and VL and then do it? VR is easy. Or can you play for the voltage directly? VC of t is that's only root, VL of t plus VR of t, that's only root. Yes, without finding this, You can't find Vc of t. Okay, so you need to integrate your current and then do it. Otherwise, differentiate the current, multiply with L, and then get this component also. Then these two add, and then you will get Vc of t. It's your call whether you want to go by integration or differentiation. So if you go by differentiation by feeling it is easy, then Vr of t first you need to find out, that is I of t into R. Then it is going to be RC into Vc of 0. Correct? I of t into that. Okay, RC into Vc of 0 into omega n by root of 1 minus zeta square into e power minus zeta omega nt into sine omega dt. You will get as it is. That's your Vr of t. Then VL of t, please. VL of t. VL of t is L into di by dt. So L into di by dt. So it's L into d by dt of your current expression. D by dt of the current expression, that is C into Vc of 0 into omega n by root of 1 minus zeta square into e power minus zeta omega nt into sine omega dt. That's how it goes. Then differentiating this, then VL of t will become L into, has differentiated. So C into Vc of 0 will be constant. Omega n will be constant. Root of 1 minus zeta square will be constant out of differentiation. None of them are functions of time. And then the result is e power minus zeta omega nt sin omega dt differentiation cos omega dt into omega d you will get. Okay. Then plus sin omega dt kept constant, differentiate e power minus zeta omega nt into e power minus zeta omega nt into minus zeta omega n. Like that it goes. Getting everyone? All of you getting?
Yes, sir.
Okay, so that's the way. So then you know your VR, you know your VL. So then find VC of t by adding the two. It's a VR of t plus VL of t. Okay, then you can find. Okay, so try this on your own. Okay, so you need to simplify this and then get your result. Okay, so that's your voltage across capacitor. Okay, we'll add them. So VC of t is equal to, what is VR of t? RC into VC of 0, VR of t first, RC into VC of 0 into omega n by root of 1 minus zeta square into e power minus zeta omega nt into sine omega dt. That's your VR, voltage across resistor. And voltage across inductor is this LC into VC of 0 into omega n by this LC into VC of 0 into omega n by root of 1 minus zeta square. Okay. E power minus zeta omega n t can be taken as common. Omega n also can be taken as common. So then take omega n into e power minus zeta omega nt as common. Tell me what is the remaining? What is the remaining? Otherwise, okay, keep it two terms. That's better. Make this expanded. Let it be better. Expand this, then VL of t will be LC into VC of 0 into omega n by root of 1 minus zeta square into e power minus zeta omega nt cos omega dt into omega n into root of 1 minus zeta square. This and this will get cancelled. Getting omega n omega n, it's omega n square. We know omega n square equal to what? 1 by LC. Will cancel this. Getting everyone? All of you getting? Following, right?
Yes, sir.
Then that is one term. Second term will become minus of LC into VC of 0 by root of 1 minus zeta square into omega n. Okay, zeta omega n into zeta omega n, minus is taken out, e power minus zeta omega nt into sine omega dt you will get. That's your second term. Okay, so first term is this. This is second term. So here also omega n is there, omega n is there. So LC will get cancelled. Okay, all of you getting? Yes or no? Following, right? Following or not? Getting or not?
Yes, sir.
Yes, sir.
Okay, then what is VR of t? Let me take VR of t here itself. VR of t is RC into VC of 0 into omega n by root of 1 minus zeta square into e power minus zeta omega nt into sine omega dt is your VR of t. We are going to add VR and VL to get VC. So what will be the resultant if we add VR and VL? Anything will get cancelled. This is plus and this is minus. Omega n is there. What is omega n? 1 by LC. Omega n is 1 by LC. So replace it by 1 by LC. If you replace it by 1 by LC, CC will get cancelled. Okay, then you will end up with R by L. R by L is, do we have R by L here? We have zeta, we have root of 1 minus zeta square. Zeta is omega n got cancelled, right? Already. My question is, are they equal? Whether this is equal to this. That is the case, they will cancel each other. All of you getting this? Getting this point, everyone? Okay, so let me add. We'll see what is the reminder. Just few more minutes, I'll conclude this. Add the 2. So if you add the 2, then VC of t will become, maybe integration is better than this addition. Try that also later. So VC of t will be VC of 0 into this component. First I will take this component, VC of 0 into e power minus zeta omega nt into cos omega dt. Then any other component, okay, no other component, that's all, one component, plus, let me take common terms in this. Let me take common terms. So what is common? E power minus zeta omega nt into sine omega dt is common in this VR and VL. I'm adding VR and VL now. So take the common terms. Vc of 0 is common. E power minus eta omega nt is common. Sin omega dt is common. So let me take the second term Vc of 0 e power minus zeta omega nt and then sin omega dt as common. Remaining is, what is the remaining in positive term? Rc by root of 1 minus zeta square. Omega n is also common, right? Is it common? Omega n common? No, it is cancelled there. So it is omega n Rc root of 1 minus zeta square is also common, right? In both the case. So divided by root of 1 minus zeta square, also common in both the terms. Here Vc of 0 root of 1 minus zeta square e power minus zeta omega nt sin omega dt is common. Rest is only zeta here, that is in the minus. Rest is only Rc into omega n here. So it is Rc into omega n and this is minus zeta. Are they equal? Rc into omega n is equal to zeta. So calculate this alone, then it is Rc into omega n is 1 by root LC. Okay, so it's no way equal to zeta. Check any mistake we have committed. That's too long. Yes, it is second order. No other choice. Any other way? Any other way? You can do one thing. Okay, you can play with this equation. Okay, you can also play like this. So this is the voltage you can find. With this voltage, we can complete the problem. Instead of going for the whole voltage, you can try for this voltage. That's another way. Things will be easier with that. Yes, it's second order. Complexity is there. Okay. So we have resistor, we have inductor, we have capacitor. Then one can go for the voltage. That's your equivalent circuit. So this is Vc of 0, initial voltage. This is L, this is R, this is your current I of t. So what I suggest you here is to make things simpler, you can focus on this voltage as Vx of t, that is plus and minus. After getting Vx of t, you can go for Vc of t. Vc of t equal to what? Vc of 0 minus Vx of t. Like that you can play. Getting everyone? All of you getting this?
Yes, sir.
Otherwise it will be lengthy. Okay, so then if you solve for this, then you'll get Vx of t plus Vl of t plus Vr of t. Okay, minus as per the current direction. This is plus minus, this is plus minus, this is VL and this is VR. This is Vx, all are same, and opposite minus Vc of 0 equal to 0. Yes, that's a wonderful root. Then Vx of t plus Vl of t plus Vr of t will be equal to Vc of 0. Then Vx of t is 1 by c integral 0 to t I of t dt plus L into di of t by dt plus R into I of t, that is equal to Vc of 0. Focuses on this voltage. Okay, so from this you can find out the current. So then your I of s will become, after taking LCM, you can find I of s, that will be Vc of 0 of s by s, Vc of 0 by s divided by, you'll get 1 by sc. Take this term to the right side, 1 by sc plus R plus SL you will get. After getting Vx of I of s already we got, we know that it will be C into Vc of 0 into omega n square by a square plus 2 zeta omega ns plus omega n square. You'll get it once again. But the goal is we are going for Vx of S now. What is Vx of S? We know S. That's how we can speed up. Vx of S equal to Vx of t is equal to 1 by C integral 0 to t what? I of t into dt. That's opposite charging alone. Let us go for Vx of S. So Vx of S is equal to 1 by Sc into I of S. Substitute I of S, then 1 by Sc into I of S is this. Okay, C into Vc of 0. That's a rapid route. Okay, C into Vc of 0 into this omega n square by a square plus 2 zeta omega ns plus omega n square. Okay, then from this Vx of S is equal to, yes, Cc will get cancelled. Okay, any mistake committed? I of S is having one C, right, in the numerator. I of S, refer the equation I of S. Okay, C into Vc of naught, Vc naught. Any S got cancelled? Yes, Vc of 0 by S. Yes, yes. Okay, this S will get, yes, that's your IC of I of S. Okay, that S is not there. Okay, this S is not there. Okay, yeah, Vc of 0 by S. Next step, you won't get it. Okay, that's fine. So 1 by Fc into I of S, that's fine. That's fine. Everything is fine. Okay, that's your Vx of S. One by Fc into I of S. That's all. Yes, the challenge is here. You need to do partial fraction. That's all. So it's going to be Vc of 0 into omega n square by S into S square plus 2 zeta omega ns plus omega n squared. Check once. Any mistake committed here? That's fine. That's correct. Okay, that's fine. That's your Vx of S. Then this will be like Vx of S is equal to Vc of 0 into, this will be like a charging transient. This will be like a charging transient. Treat this as a step input of 1 by S, and this is your system. Then it is 1 minus e power minus zeta omega nt by root of 1 minus zeta square into sine omega dt plus theta you will get. That's all. That's your Vx of t you will get. And then you can go for Vc of t from this. Vc of t is Vx of t. That is Vc of 0 minus Vx of t. That's all. Okay. Yes. So then Vc of 0 will get cancelled because of this one. Rest will follow. Yes, that's a final result. Then Vc of t will be Vc of 0 into e power minus zeta omega nt by root of 1 minus zeta square into sine omega dt plus theta. That's all. That's voltage. Reading everyone?
Yes.
Reading everyone? Yes. So try this route is faster comparing to the last route because it's not easy conclusion. But anyway, there's a point where you need to minimize. Okay. So here you can't compete instantly. Okay. Check this route. Okay. That's a final point. Okay. There you can get Vc of t easily. Simplify. Try to simplify this. Okay. Another route is this route, changing the perception of the problem, get Vx of t quickly by using current, and then finally go for Vc of t as a function of Vx. That's another way. Fine, everyone. Following.
Yes, sir.
Okay, little lengthy. Yes, then plot what is really happening to your voltage. Time t equal to 0. Time t equal to 0. What's voltage across capacitor?
T of 0.
Yes. Time t equal to 0. Vc of 0 plus. T equal to 0 means it is sine theta. Sine theta is equal to root of 1 minus zeta square. Our cos theta equal to zeta. Remember that. So then sine theta root of 1 minus zeta square will get cancelled. T equal to 0 e power minus 0 1. It is going to begin with Vc. It has to begin with Vc of 0, Ashwath. Getting?
Yes.
Capacitor begins discharge. It has to begin there only. Then it is going to begin a discharge that is equal to 20 volt. Okay, as per our problem. Initially discharged to 20 volt long before. Then the time begins for the discharge. Then it is going to discharge with this transient. Then the transient, discharging transient will be this. Okay, it will fall and oscillate. Negative also possible. And then will reach 0 after that time 5 by zeta omega n seconds. Getting everyone? Yes. Like an impulse response. But impulse response doesn't begin with the finite value. This is beginning with the finite value. That's the difference. Okay, this theta makes all the difference. If this theta is not there, entire function will become 0. Getting? If this theta is not there, if t equal to 0, entire function will become 0. Getting everyone? Following, right?
Yes, sir.
Yes, Fadil, clear?
Yes, sir.
Okay, so that's a way. So little complex, but still, okay, you need to get it done. Okay, so change in perception makes a problem instant. Okay, so try both the routes once again. Okay, so after going through the slides. So it's time for lunch break now. Yes. Yes, right? You need, right? You need or
Yes,
not?
sir.
Okay. So have your lunch. We'll meet after 1 hour. Okay.